Hi, my name is Gunjan Vasantaramtike, and today I will present my research titled Calibrated Multi-Branch Learning for Cancer Risk Predictions, comparing tabular transformers and gradient boosting ensembles and demographic bias auditing. This work focuses on improving cancer risk prediction using machine learning while also ensuring fairness and trustworthy probability predictions with clinical healthcare systems. Moving on to next slide two, which is introduction. Cancer is one of the leading cause of death worldwide, so early risk predictions is very important for better treatment and patient care. Machine learning models such as XGBoost and LightGBM are commonly used for clinical tubular data because they provide strong prediction performance. However, two major problems still exist. First, many models produce poorly calibrated probability predictions. This means the predicted probabilities may not correctly reflect the true risk. Second, demographics bias can occur where model performance changes across groups such as age and gender. This can reduce trust and fairness in healthcare application. To solve these problems, this research proposes calibrated multi-branch learning framework that combine TabNet, FT transformers, and XGBoost plus CatBoost assembles models. The framework also applies temperature scaling for calibration and demographic bias auditing modules for fairness evaluation. Moving on to slide number three, which is related to related work. Earlier cancer prediction studies mainly use a traditional machine learning methods such as logistics, regression, decision trees, and random forest. Later, gradient boosting methods such like XGBoost and LightGBM became popular because they achieved higher accuracy on structured healthcare dataset. Recently, transformer-based tabular models such as TabNet and FT transformers have shown strong performance and better feature learning capability. Some studies also used explainable AI methods like SHAP to improve model interpretability. However, most previous works focused on mainly on prediction accuracy. Very few studies evaluated calibration quality and demographics fairness together. This research addresses both problems within one unified framework. Moving on to slide which talks about methodology. I'll explain the methodology used in this research. As shown in the figure, the proposed framework contains three parallel learning branches: TabNet, FT Transformer, and the XGBoost plus CatBoost ensemble. The process starts with pre-proposed clinical data collected from 1,500 patients recorded with 23 clinical features. Several pre-processing techniques were applied before training the model. These include KNN imputations for missing values, label encoding, quantile normalization, and smooth balancing for minority classes. The first branch is TabNet, which uses sequential attention to select important features step by step. This helps the model focus only on the most useful clinical information. Second branch is the FT transformer model, and it learns the relationship between different features using self-attention mechanism and similar to transformer model used in natural processing. The third branch combines XGBoost and CatBoost ensemble learning models. These models are strong for structured healthcare data sets and improves uh, prediction stability. After each branch generates prediction probabilities, temperature scaling is applied. This calibration step reduces overconfident prediction and improves probability reliability. Next, the calibrated outputs are passed to the demographic bias auditing model. This module evaluates fairness across gender and gap groups using SPD and EOD metrics. Finally, the framework generates the final cancer risk prediction classified into low, medium, and high risk categories. This complete pipeline helps achieve accurate, calibrated, and fair clinical prediction. Moving on to slide number four, which talks about methodology. The study used cancer prediction data sets containing 1,500 patient records and 23 clinical features. The target class were divided into low, medium, and high cancer risk levels. Several proposing steps were applied, including KNN imputations, label coding, quantile normalization, and smooth balancing. The proposed framework contains parallel branches: TabNet, FT Transformer, XGBoot, plus CatBoost Ensemble. TabNet uses sequential attention to select important features step by step. FT Transformer learns features relationship using self-attention mechanism. After training, the temperature scaling was applied to calibrate prediction probabilities and reduce overconfidence. Finally, a demographic bias auditing model evaluated fairness using SPD and EOD metrics across gender and age groups. Moving on to the next slide. I'm sorry, which talks about results. The proposed framework achieved 93.8% accuracy and macro F1 score of 0.931. It outperformed all baseline models included in the study. The framework also achieved an AUC-ROC score of 0.971 and Cohen's Caper score of 0.897, showing strong classification reliability. For the for the high-risk cancer category, the proposed model achieved better recall and F1 compared to XG boost and FT transfer on baseline. Temperature scaling and significantly reduced calibrated errors. The final expected calibrated errors were reduced to only 0.019, which indicated high reliability and high reliable probability predictions. The demographic bias audit also showed that proposed framework successfully passed fairness thresholds for both genders and age groups, while baseline models failed to at least subgroup test. Overall, the results demonstrated balanced performance in terms of accuracy, fairness, and calibration. Moving on to conclusion here. In conclusion, this study proposed a calibrated multi-branch framework for cancer risk prediction using clinical tabular data. The framework combines transformer models and gradient boosting techniques to improve prediction performance. It also addresses two important healthcare AI challenges: probability calibration and demographic fairness. Experimental results showed that the proposed system achieved high accuracy, reliability, probability estimates, and fair predictions across patient groups. This makes framework more trustworthy for future clinical decision support system. For future work, a larger multi-center data sets and longitudinal patient records can be used for further improved model generalization and fair evaluation. Thank you for your attention. Happy to answer any questions.